you're the only one mic'd, it's important if anybody has a question to try and restate. I know Oliver will get one.
I will try to remember. I'll probably forget.
So there's two moving boards on each one. It's good to use the moving ones because the very bottom you can't see from the back.
Yeah, so I use this one.
So use this one and then the one under it. Yeah, but I would say don't use this.
No.
That doesn't
Okay. This is the hardest part of lecturing, the Blackboard management.
Blackboard management. Yeah, that's why I'm trying
Yeah.
to internalize the lessons and
Yes.
replicate them to the next speaker. I'll bug you about repeating questions.
Yeah, I'll forget. I'm sure I'll forget.
Everybody does. Some of them learn after 3 or 4.
Yeah, probably by Thursday I'll know.
Some of them never.
Yeah, well.
They know this function exactly, so in principle it contains a lot of things.
As he said, it pins down regular modules.
Just give it another minute or two.
Yeah, no, I...
Started for the afternoon session. So our next set of lectures will be Jaume Gomis talking about supersymmetric localization.
Okay, so thank you very much. It's a pleasure to be here. So I was given the title of my lectures to be localization. So let me tell you what I will actually try to lecture on in these short lectures. So essentially the thing I want to do is to explain to you certain fairly recent results that have led to something that sounds like a theorist's dream, which is the exact computation of observables in quantum field theory that led to when you study quantum field theory, you learn that very early on that you have to be a bit humble, and that in principle, in general, we do not know how to study or compute observables in the theory beyond, say, perturbation theory, let alone compute observables as an analytic function of the coupling constants of the theory. So the point is that in recent years, it has been possible to do this in certain supersymmetric quantum field theories. I understand that last week you had lectures on supersymmetry. If something more broadly said, You should stop me whenever I say something that's not clear or I'm too clear. That never happens. Stop me and ask questions. But I understand that you have some basics about supersymmetric field theory. So what happens here? So in quantum field theory, we'll have some correlation function, say, of a bunch of operators. I'm not committing whether these O's are local operators or line operators or surface operators. It doesn't matter. And this is defined, this is a schematic because by some path integral and this integral is a very much infinite dimensional integral that we do not know how to solve exactly by any stretch of the imagination. Now the miracle that supersymmetry allows you to enjoy is that in the right circumstances, you're able to reduce this integral. You can do this integral exactly and reduce it to essentially to a finite dimensional integral. So we went from an infinite dimensional integral to a finite dimensional integral. And this integral is an exact representation of the answer for this observable for all values of the coupling. So there is an analytic formula for certain observables that you can compute as an analytic function of the coupling. So if you say you're interested in the coupling with 0.1, you evaluate the integral for 0.1. If you're interested at 1, then you can, usually, of course, we don't know how to study theories in the strong coupling regime. But since we managed to reduce this to a finite dimensional integral, you can ask questions about what happens to those observables at strong coupling. Okay? And so, the key insight, or the key technique that allows you to do this, that's where the buzzword upstairs comes, is supersymmetric localization. And the word localization just means, for now, that we reduced the space of where we integrate over, which is infinite dimensional in all possible ways, to a finite dimensional space. Okay? So we localize from an infinite dimensional manifold to a finite dimensional manifold. Now, so last week I believe that you had lectures on supersymmetry, and there you already saw that holomorphy was used in an important way to constrain certain correlation functions. The thing that's important about here is that these observables are non-holomorphic observables. So they are not constrained by holomorphy. So I think it's fair to say that if you were in the early 2000s and you would have asked someone, will you ever compute, is there a chance to compute some non-holomorphic observables in quantum field theory, in supersymmetric quantum field theory exactly? The answer probably would have been no. But now there's a large class of observables that we can compute in various dimensions with various amounts of supersymmetry, and that's what I will touch upon during this course. Okay. So right now I'm just giving you kind of an iBird view of what I'm going to talk about, then I'll get more concrete, of course. So of course, having the exact results has led to many new insights into the monsters of strong coupling that we usually don't know how to access. So having explicit results about this has led to new insights into various things, including strong coupling. For example, asymptotic series, imperturbation theory, dualities, and also mathematics. It turns out, as one of the interesting outcomes of these exercises of doing this, is that essentially doing this work and computing these observables has led to answering long-standing mathematical problems using physics-based methods. So things that mathematicians couldn't do really directly, using these supersymmetric localization path integrals, we can answer questions that they were interested in. and they are relevant for string theory. I may discuss them later in the course. Okay, good. So this is an extremely broad subject, so I have to choose some logical path. So the way I did it is I looked at the lectures last week, and so there were essentially two basic topics last week. One was conformal field theory, which is still ongoing, and the other one was topological field theory. So the main thing I'm going to focus for most of the lectures, even though this can be generalized in all possible directions, I'll be studying supersymmetric conformal field theories. Okay. Many of the things I will say about exact results can be extended to massive theories that are not conformal. As you know, massive theories, after all, are just deformations of supersymmetric field theories, but for the nice, things will be maximally nice for conformal field theories. Okay. So there will be two central themes in these lectures. So one of the important advancements in this has been to study quantum field theory not in flat Minkowski space that we usually study in textbooks, but actually to try to do something that a priori looks not interesting if you're a person that is married to flat space, which is to study these quantum field theories coupled to a curved background, like the sphere. Okay. So this is something that you can try to do. But then if you're a physicist, it's interesting, even if you don't know what it means, you can still, if you can compute it, you should do it and see what you learn from it. But one of the things that we will study is to see how certain partition functions of conformal field theories on spheres, round spheres, so Sn is an n-dimensional sphere, how these guys compute certain observables, correlation functions of theory in flat space. RD. So if you're a hard-nosed person and you only care about RD, the point is that Rn, I guess. Let me put that here. D. It is in your interest to study this object because this object we can define and compute explicitly using the things that we'll explain. And this will compute as an exact analytic expression observables about the theory in flat space. I will explain to you how this comes about, hopefully in this lecture already. So this is one step. It's just telling you, making identification between what quantity does this object compute, the sphere partition function of the CFT on the sphere, corresponds to which observable of the theory in flat space. That's step number one. Of course, doing this is great, but if you're not able to compute this, it's not very useful. Okay? So the second step will be to learn how to compute the partition function of the CFT on the sphere by SUSY localization. Okay, and in the rest of the lecture, I will describe the first point. Any questions about kind of the plan of where I'm going? Okay. So first, I'll introduce some ingredients that are basic to conformal field theories and the generalized objects that you have already seen, presumably seen before. So in a conformal field theory, we have primary operators. And in particular, primary operators are labeled by the way that they transform under scale transformations. If I make a scale transformation, x mu goes to alpha x mu, an operator of dimension delta will transform in this way. Okay? Where delta is the scaling dimension of the operator. Okay? And we know that you can essentially organize the operators according how they affect the theory in the infrared. depending whether the dimension of the operator is less than the dimension of space-time. These are the relevant operators. These are the irrelevant operators. If the dimension is bigger than the space-time dimension, they're irrelevant. And when it's the same, they're marginal. So these two break, if you deform your theory by these operators, they break conformal invariance, if you start with the conformal field theory, while if you perturb by this operator, it doesn't. It preserves conformal symmetry. So let's study the following object. Oh. So let's start with a putative CFT, and let's allow the most general deformation of that CFT by all possible marginal operators, okay? So this would be a submanifold in the space of all quantum field theories that preserves conformal symmetry. So let's study the object, Z as a function of lambda I. So lambda I are the coupling constants that are conjugate to the exactly marginal operators. And you could imagine of defining this object in this way. So you start with a putative CFT, let's call it CFT naught, and you can explore the space of all CFTs by perturbing that CFT by this operator, where lambda I is the coupling constant and OI, so OI is an exactly marginal operator. So these coupling constants define a space, which is the space of all the space, so these lambda i's. Well, this object defines the space of conformal field theories. And this guy is a manifold we're going to call M. This is also known as a conformal manifold. So this is the subspace in the space of all quantum field theories where conformal symmetry is unbroken. Okay? Now both the couplings and the operators admit a natural geometrical interpretation in this language. Lambda I are obviously local coordinates on the space. So here I have this space. I started with this putative CFT and I deformed in some direction, and there are some coordinate lambda here. Okay? And the exactly marginal operators I are tangent vectors or sections of the tangent bundle. Okay? So these are infinitesimal deformations that move you away from the putative CFT. Okay? So one goal that we would like to have is to be able to compute. So goal is compute observables throughout all M, everywhere in the conformal manifold. So as an exact function of this coupling is lambda. Now typically this is impossible, and at best we can have an approximate solution to this question where say lambda is very small and we can use some kind of perturbation theory. The goal here will be to try to compute observables that you can analytically give an analytic expression for being anywhere in this manifold. Okay? Good. So this conformal manifold has a geometrical structure associated to it. I already told you that the geometric interpretation of the couplings and the operators. But actually there's a canonical object you can define here, which is you can define a canonical metric on this, which is known as the Zamolodchikov metric. And essentially the way it's defined is that you take the two-point function of two exactly marginal operators. So I'm always going to use this notation of O Latin I for exactly marginal operators. Okay, so this is so this doesn't turn into a monologue. Can someone tell me what the power here would be? X to the 2d, yeah. And the coefficient here is exactly the metric. Okay. And now you can convince yourself that that if I do a change of coordinates, that under a change of coordinates, coordinates means coupling constants from the physical point of view, from lambda I to lambda I tilde, that indeed this object Gij transforms as a metric. Okay? Okay. So there's this canonically defined object on of a CFT, if that CFT has exactly marginal operators. It has a Riemannian metric that's completely determined by the two-point function. Here we are in flat space still. Okay? So then let me say a few things. So first of all, this is a fundamental and canonically defined object. And it greatly generalizes the conformal anomaly that you may have seen or you will see. Which, remember, that the conformal anomaly is defined, say, in 2 dimensions from essentially the two-point function of the energy momentum tensor. So I'm being really schematic. So this object is also computed by a two-point function, but in a sense this object is much richer than this one, because C, even if you have a space with exactly with marginal operators, C is a constant. Namely, it's the same everywhere in the conformal manifold. It's a constant on the conformal manifold, so C is constant on M, while this guy is a very non-trivial function of lambda. It depends concretely on where you are in the conformal manifold. And actually, we will see, hopefully tomorrow, that in fact there is a rather elegant way in which you can think of this Gij as coming from a more general understanding of anomalies, of conformal anomalies in conformal field theories. This guy can also be thought of as an anomaly in a certain sense that we'll describe tomorrow. Okay. So we have, yes.
Do we know anything about Gij? Like, is it flat or?
We know some things, but very few things, in fact. And one of the goals of these lectures is to give a way of computing Gij exactly. Okay. Yes. Sorry, here? Yeah, so, yes, thank you. So the question is, here am I computing at one point or everywhere in the conformal manifold? And the point is, something that you can show, and we will show explicitly tomorrow, is that the Euler anomaly, which is the one that appears here, you can prove by a basic consistency condition of anomalies called the Wess-Zumino consistency condition, that C is a constant on the conformal manifold. So actually, this is true anywhere. Is that what you asked?
Yeah, and also the one above.
Yes, of course. It's a function of lambda, yes. Yes. The point I wanted to make is that the lambda here dropped out here just by some properties of anomalies.
So these operators for I that are exactly marginal, couldn't they also depend on lambda? Like depending on what point and the direction, the marginal direction can have shifted?
Yes, and then you have to worry about, yeah. The question is whether the operator could depend on lambda, but then you can do change of coordinates. There is a way of parameterizing in which things that you have to worry about this issue. Yes, yes.
Differentiating between theories with different content and all, or is all part of the same manifold?
field content. No, so what field content? So here, if as lambda and lambda is in your head, we should not be, in a CFT, you should not be talking about Lagrangians, okay? We're talking about some abstract object that has satisfied certain axioms. Now, what can happen is that, okay, so what can happen, actually, no, this is the point I'm going to describe now maybe. So what can happen is the following, is that you have this conformal manifold. And if you wish, different points in the conformal manifold could have a better or more perturbative representation using different field content. But it's all part of the same CFT. So it's like you have a manifold, you have coordinate charts. You could describe the physics in different coordinate charts. And in one language, that would be describing the physics using one Lagrangian, and the other one would be describing the physics in a different Lagrangian. In some corners in the conformal manifold, certain Lagrangians are more so in one description, the Lagrangian would be the description would be perturbative. In another one, it wouldn't be. So related to this point is that you can have that symmetries and dualities can act on M, on the conformal manifold, and therefore the space of inequivalent conformal field theories, so the space of inequivalent CFTs reduces to what I will use the word fundamental domain. Any theory outside the fundamental domain can be related to the theory inside the fundamental domain by some kind of duality transformation. Okay? So let me give you, so this doesn't sound so abstract, let me give you examples of theories that you know that, of theories that have a conformal manifold. Okay? So existence of a conformal manifold. So one example that you may have seen is, let's take two-dimensional conformal field theories. Okay? A conformal field theory, and let's take the theory of a compact scalar. So this is a CFT that has C equals 1, and the action is d phi square, but phi is a compact variable, so phi has an identification of this type. Okay? So this theory is free, so we know absolutely everything about it. Now, naively, you would say that the space of conformal field theories is labeled by a semi-infinite line, because R can go from 0 to infinity. But this theory has a famous duality. It depends on which community you come from. It's called different in different ways. In one way of saying that there's a T-duality symmetry that identifies the theory at radius R with the theory at radius 2 over R. Okay? So that means that if you have, so the fixed point of this transformation is R is root 2. So this means that, okay, so I draw the real axis here. There is the point root 2, and any point out that's bigger than root 2 can be mapped inside this fundamental domain from 0 to root 2 by this T-duality transformation. So this is an example of a theory that has a duality, and the space of inequivalent conformal field theories is obtained by quotienting the naive conformal manifold by this duality symmetry, and you get just an interval. Okay? And this theory has interesting points. At root 2, you have an SU2 symmetry. At 1, this is dual to a Dirac fermion. At root 2 over 2, it describes the Koster-Lithauses transition, so on and so forth. Okay? Since this theory is free, this is one of the few examples where we can compute the dream of compute the observables throughout all the conformal manifold. For this theory, since it's essentially free, we can compute whatever you want at any point on the conformal manifold. Okay? So that's an example of a theory that has a conformal manifold. Okay. Now, later in the course, we will study two-dimensional superconformal field theories that are strongly coupled, which means that they are not free. They're, in fact, highly nonlinear. And they have a conformal manifold. And one of the goals will be, so later we will describe strongly coupled two-dimensional CFTs that have a conformal manifold, but which nevertheless we will compute these correlation functions everywhere on M. Okay? Yes?
This might be overly pedantic, but depending on how you define conformal manifold, the C equals 1 theories have a bigger conformal manifold than that. So are you?
Yes, yes. Are you saying, so there is a, at root 2 over 2, there is a new exactly marginal direction that opens up. Yeah.
So are you like forgetting about these things that make it a...
No, no, I won't forget about anything, but for the... No, but this was a point, it's a very good point. So for those people that don't know, this is a particular point, there is a new exactly marginal deformation that comes up that can be thought of as an orbifold radius. And then, yes, so you can do that. Now, in the theories that we will study, this kind of situation will never occur. You will really get some nice manifold, and marginal operators will not appear and disappear out of the vacuum. There will be a fixed number throughout. Okay, but yeah, that's a very good point. So here there is a new theory that comes up, and there is a fourth. If you know what that means, there is a four-state Potts model somewhere up there. You know, some horrid things like that. Yeah.
What about the archipelago in this picture?
Archipelago.
Ginsburg's TOE.
Oh, they're also there. Yeah. Yeah.
But, so every case that we see will be connected?
Yeah. Yeah. And you can prove that. You can prove that such weird things don't happen. Yeah. Okay. So this was an example in 2 dimensions. Now let me give you examples in 4 dimensions. So let's consider 4-dimensional gauge theories. I'm going super slow, but that's life. Okay, so this theory has a classically marginal complex coupling. It can be parameterized by a variable tau, which is theta over 2 pi plus 4 pi I over g squared. Now, since g squared is positive, the coupling constant tau takes values in the upper half plane. Okay? Now, what is the operator that couples to tau? Okay, so I should maybe tell you what theta is. So theta is the topological angle of QCD and couples to F wedge F. And g squared is the Yang-Mills coupling constant that couples to F star F. Okay, these are the 2 Lorentz invariants that you can write down in 3 plus 1 dimensions. Okay. Now, what is the operator that couples to tau? So what is the Lagrangian of the theory? What is the operator that couples to tau? So you can write the Lagrangian as tau O plus the complex conjugate. Because O is complex, right? And the Lagrangian, I will do all we can that Lagrangians are real. And O, you can check that O is, forgetting about factors of 2 and all of that stuff, is a trace of F minus I star F squared. Okay? And you can show that if you use these definitions that you get, in fact, the Yang-Mills Lagrangian. Okay? Now, let's compute the homologic of metric in this theory. So I have to compute the 2-point function of this object. O. Okay, so what? Okay, so let's compute the homologic of metric. Can someone tell me, just from perturbation theory, what would be the metric? Can someone tell me? So that I don't speak to myself. Can someone tell me what goes here? Just from Feynman diagrams. old-fashioned Peskin and Schroeder, or Ramon left, but he has a textbook. Who said that? Yeah, so can you explain why? That's the right answer, but
Well, you could just write that.
yeah, so what's the propagator?
1/m².
No. 1/m tau.
Oh, yeah.
So there are two of them. Yeah, so here, just because the propagator of the gluon goes like g squared, which is 1 over the imaginary part of tau, and when you connect two of these guys, you're computing essentially a two-point function of this guy, there will be two propagators, and from here you're going to get the imaginary part of tau squared. And this is nothing but, so this is classically, or at leading order. And this metric, if you know anything about ADS-CFT, is just the Poincaré metric, or whatever it's called, in the upper half plane. It's the negatively curved metric in the upper half plane. Okay. Now, of course, in real Yang-Mills, tau is not an exactly marginal coupling because of virtual corrections make tau run. So it's not a conformal field theory. But there exist many four-dimensional superconformal field theories where tau is marginal, exactly marginal. So the most famous example is the most symmetric example, which is n=4 super Yang-Mills. So I don't know if you've been exposed to this yet, but this is the canonically maximally symmetric theory you can write down in 4 dimensions. It's the most symmetric theory you can write down in 4 space-time dimensions. Okay. And now you could ask, okay, so this was a computation that we did at one loop. What happens at higher loops? What happens with instanton corrections? Blah blah blah. So one of the things that we will see from localization is that actually this guy, the metric, is exact. The Poincaré metric is exact. There are no perturbative and no non-perturbative corrections to this metric. And now there is an infinite family of n=2, calligraphic n=2 superconformal field theories. So these are, you were introduced last week to theories with extended supersymmetry, or at least some aspects of it. And now here, you would want to know what happens to the Zamolodchikov metric as I move in the conformal manifold. By the way, you can have theories that have more than one coupling constant. Imagine you have two gauge groups, for example. You could have a two-dimensional complex manifold, one associated with one gauge group, the other one associated with the other gauge group. So one of the things I would like to do is, what is the Zamolodchikov metric anywhere in this, for example, in this upper half plane, okay? And it turns out that using this localization, there is an exact expression that computes this quantity, and there are corrections. If you are a perturbative person, there are corrections to all loops and instanton corrections to this quantity. Okay? Then now we can compute using these finite dimensional integrals that we will derive. Okay? And more concretely, there is an analytic formula for that. Okay? Now, these theories, both n=4 super Yang-Mills and n=2 SCFTs, just like the example of the compact boson, also have a duality which relates theories at different values of tau. And then the fundamental domain, you can map the theory from the fundamental domain to from the upper half plane to a fundamental domain. So for example, for n=4 super Yang-Mills. So these theories have S-duality. So this is some symmetry group gamma. And then the fundamental domain is going to be the upper half plane divided by gamma. So for example, if you're doing n=4 super Yang-Mills, essentially gamma is SL2Z. And then the fundamental domain is famously this picture. A fundamental domain is this. You can map everything inside here. Okay? So this is the space of inequivalent four-dimensional n equals 4 superconformal field theories. Okay. Good. Now, there are more operators in life than exactly marginal operators. And one of the things that we will want to do is also try to learn how to compute correlation functions of other operators as you move in the conformal manifold. So let me say a few words about this. I'm still kind of setting up the geometry of how to think about operators in these theories. Okay. So it turns out in a conformal field theory, operators can be thought of this chalk is falling on me, can be thought of as sections of some vector bundles over the conformal manifold. Okay? So an example, for example, would be the exactly marginal operators, OI. Which bundle describes the exactly marginal operators? Can someone tell me? The tangent bundle. So OI would be the sections of the tangent bundle. But more general would be other interesting bundles that you can define given a collection of operators in the CFT. Okay? Now what you can do is take these operators and do parallel transport along the conformal manifold, okay? And ask, so actually doing parallel transport along the conformal manifold induces some operator mixing. As we parallel transport. And this parallel transport is governed by a connection, like you're familiar from general relativity. And that connection is actually literally very similar to the Berry connection of quantum mechanics, where you have a state and you ask what happens to the state when I move parameters and you come back. There's a certain connection that computes what happened to that state. The same thing happens with these operators. Okay? And the curvatures of these connections, you have a connection, you can compute the curvature of the connection, and that computes certain topological information about the vector bundles of the theory. And later in the lectures, hopefully in the last one, I will tell you how to compute correlation functions of other. Okay, so this would be more. These OIs need not be exactly marginal operators. It will be some special class of operators. These are called chiral and antichiral operators that you can define everywhere in the conformal manifold, and we will find a way of computing their correlation functions anywhere in the conformal manifold, and in particular determining the curvature of these various vector bundles. Okay, very good. So now we start getting more into business. So how are you going to do this? So one of the key ideas or techniques that have gone into solving this problem has been to do something that a priori seems that has nothing to do with the problem we're interested in. Here we're interested in computing correlation functions of the theory in flat space. Okay, I want to know the 17-point function of some operator in flat space. Okay, and but the route to solving this problem has been to study the conformal field theories on some curved manifold. Okay. Now, if I tell you what the partition function of a CFT is on a curved manifold, you may not immediately be able to tell me if this has anything to do with an observable in flat space. Okay. Now, there are some examples in which it's obvious that it has something to do with an observable in flat space. So imagine that we compute the partition function on a geometry that is circle times some manifold Y. And now imagine you go to a colleague across the corridor that's not a crazy theorist, and you want to explain to that person, to give it a more physical interpretation of what this quantity is. So can someone tell me what this compute say in some Hilbert space language? Okay, I heard the word trace. Oh. Trace? Eta minus beta h of the Hilbert space of the theory on a manifold Y, right? Now, and depending whether fermions are periodic or anti-periodic, you may add, if they're periodic, you would add here a minus 1 to the f, which I believe you saw that last week from your lectures, okay? So here we know. Now let's tackle the following question. So a conformal field theory, so what's a very general canonical geometry in which you can put a conformal field theory? Any CFT can be canonically placed on a d-dimensional sphere because by a stereographic projection, essentially. By a stereographic projection. So a conformal field theory famously does not depend on the overall scale factor. So I should be able to place, if I have a CFT, that's not true of a massive theory, but a CFT, if there's a canonical way to go from the theory in flat space to the theory on the sphere. Because the metric on the sphere is essentially conformal to the metric in flat space. So this would be in stereographic coordinates. Okay? Good. So now we should ask the following question. So here we were able to answer what was the physical interpretation of this quantity. Now what we want to ask is the following. So we know that we can canonically plot CFT on the sphere. The question I want to ask is, what is the physical meaning of the partition function of a CFT on a sphere? So now I will start explaining this. Okay. One thing I should mention is that in these lectures I will try to introduce ideas and techniques that are more broadly applicable than just supersymmetry, because I think they're important. And what I'm going to discuss now is an example of that. Okay. Of things that you should know, essentially, which I feel you should know. And that anyway are helpful to answering this question. I'm not just doing it because, yeah. Okay. So let's think a little bit about, more abstractly about quantum field theory, okay? So we want to compute this object. So the first thing that we say immediately is the following. So we put the theory on a compact manifold. One great advantage of this is that this observable will have no infrared divergences. So that's good. We don't have to worry about that. Now, will the theory have ultraviolet divergences? Yes or no? Yes. So because ultraviolet divergences have to do about short distance physics, and you couldn't care less whether you're in flat space or on a Calabi-Yau manifold. You're going to get a divergence. So there exist ultraviolet divergences. So if we're going to study if we're going to try to answer this question, we will have to worry about defining this quantity as a renormalized. I mean, quantum field theory, you have ultraviolet divergences. You have to, in order to define an observable in the continuum limit, you have to study the regulated theory, are local counter terms to cancel all divergences, and then take the continuum limit and see what you get. Okay. So let's proceed with that. Okay. Now, one thing you may worry about, and you should always worry about this, is that when you have an observable in quantum field theory, you may want to know whether that observable is scheme independent or not. What do I mean by that? there are observables or patterns of the observable that depend on your choice of regularization scheme. You regulate your theory using polyvillars, I regulate it using something else, and you will get different answers. Things that depend on the regulator we call scheme dependent, and we don't care about them. Okay? So we're going to fish out here for quantities that are scheme independent, that any two persons using whatever regulators will agree on the answer. Okay? These are quantities that are intrinsic to the conformal field theory. They don't depend on some choice of regularization scheme. So let's start with some dimensional analysis. And it turns out that the answer will depend very sensitively whether we're in even space-time dimensions or odd space-time dimensions. Let's be in even dimensions. So let's study. And now imagine I introduce a hard cutoff, lambda, and I have a sphere of radius r. Let's study the possible dependence of the log of the partition function, roughly the free energy, the dependence on the UV cutoff, the radius r, and the exactly marginal couplings. Okay? So obviously, there's going to be short distance singularities. Can someone tell me how the leading ultraviolet divergence will scale with lambda? Someone is doing this with the finger, but I don't know what that means. Oh. They have to answer it. Okay. No, so ultraviolet divergences comes whenever you have coincident point singularities, right? So if you study the theory on a manifold, I don't know how to say it without telling you the answer already. So that's the problem. You know this, okay? Sorry? Yes, no, but I'm asking concretely, with what power of lambda does the leading divergence go? Yeah, exactly, yeah. So it would go with lambda times r, because we need a conformal field theory, lambda and r always come in pairs, to the 2n, times some function a of n of lambda. Okay, which we don't know what this function is. I'm just parameterizing the divergences. Now, what will be the next subleading divergence? Can someone tell me? Sorry? -2 or -1? It was -2. I was just trying to trick you, but you will have to explain me why it's like that. Okay. And then we go all the way down to. So this is even. So the power of the divergence goes down by a power of 2, all the way down to a finite term, f of lambda. Okay. So actually, it turns out that in even dimensions there is an extra term that's very important that you can have that depends logarithmically on the radius, which we'll call a of lambda log of r lambda. And this term is there because of the conformal anomaly. I may elaborate this in a second. Okay, so now there are several things I want to do. First, I want to know, can I eliminate all ultraviolet divergences by local counterterms? And if so, what are the local counterterms? So can someone tell me which local? So in a conformal field theory, when you do perturbation theory, what you do is you may have to tune local counterterms to satisfy the conformal word identities. Okay, so you have to. You're familiar that when you tune to a fixed point, you have to fine-tune certain things, right? So which term do I have to fine-tune to kill this divergence? Can someone tell me? That's a cosmological constant term. So it will be something like d to n x square root of g a n lambda. What about this one? Sorry, here is p2. Yeah, what about this one? Which local counter term do we have to add to cancel this divergence? Yeah. And that's why it goes by powers of, it goes down by powers of 2 and not powers of 1. Okay? So the point is that up to here, I can remove all the power law divergences by using vanilla local counter terms, the cosmological constant, Einstein-Hilbert, and higher powers of the curvature. Now, what about these two? Well, this one is finite. Okay, so we have to discuss whether this finite power is physical or not physical. And we have this logarithm. Okay. Now, something and I guess I will discuss this more systematically tomorrow about anomalies. Anomalies, by definition, this guy is there because the theory has a conformal anomaly. Okay. So in even dimensions, there is a conformal anomaly, which means the trace of the energy momentum tensor is not 0 once you couple the theory to gravity. And there is a coefficient which is A of lambda times the Euler density. There are other things, but these other things are not important for this discussion because all the other terms are while invariant and the while curvature of the sphere is 0. Okay? Euler density. So this is something that you construct out of the Riemann tensor that has the property that the integral over this defines the Euler number. Okay? So this is an anomaly. Okay? And essentially an anomaly is almost by definition an object that cannot be removed by any local counter term. Okay? So no matter what I do, I will never be able to get rid of this coefficient, of this term, unlike the power law ones. By virtue of this being an anomaly. It's almost a definition of an anomaly. Okay? So this guy is physical. Physical in the sense that there is no, two different regulators will not change this coefficient. Okay? And it's an exercise that I will leave to you, that if I change the radius of the sphere from r to delta r, and I integrate, okay, so another way of writing this anomaly is as this, is to say that under a Weyl transformation, the log of z is the same as the integral over of this. Okay? Now you can prove that under such a small shift of the radius from r to delta r, that delta of the log of z, so the integral of the Euler density over the sphere is 1, exactly 2, but whatever, it's 1. And delta sigma is just delta log r. Okay? Essentially, it's delta r over r. Okay, I'm going a bit fast. If things are not clear, you can ask me for how to derive this more. It's completely straightforward. And from here, you get a of lambda delta log r. And integrating this equation, you get precisely this. Okay? So the existence of a conformal anomaly predicts that there is a logarithmic dependence on the radius of the sphere. And this coefficient is the Euler anomaly. Okay? Fine. So there is this term. Now you may think, is this guy physical? The finite part is physical. Oh, and I think that one thing that's very important is that this a of lambda that appears in the anomaly, a is a constant on the conformal manifold. Okay? And this again follows from a Wess-Zumino consistency condition that I will describe tomorrow. So far we've discovered that there is one number, A, that's scheme independent. Any two persons that don't make mistakes will get the same number. And that's physical. Now we have a more interesting function here that could have a lot of information, and we want to ask, is this quantity is this quantity scheme independent or not? So how do we determine that? we have to compare two different regulators, and two different regulators are distinguished by the choice of local counter terms, okay? So if I can write down a local counter term that I construct out of the background metric and the coupling constants that is marginal, then this guy is not physical. But the point is that there is. I can add, so imagine you compute in one regularization scheme, and I choose a different regularization scheme. And in my scheme, I'm allowed to add the following local counter term, which is just an object that you construct out of the background fields, the metric and the coupling constants. So if I add this to my partition function, to my functional integral, I can add this following a gadget. So d to n x, square root of g, e to n, f of lambda. Okay? I can always add with an arbitrary coefficient this guy in my functional integral. It's a perfectly well-defined regularization scheme. But then if I do that, my partition function z, this goes in the exponent, right? And the integral of the Euler density over the sphere is 1. So that adding this counter term will give you an ambiguity. This is an ambiguity in z. Because z, by adding or not adding this term, I change my partition function by an arbitrary function of lambda. Okay? So that means that this quantity here that we thought was physical is not physical at all. I can always remove it by a choice of local counter term. Yes?
That's why you were restricting to 2n?
No. Well, yes and no. But yeah, so the question was, is this why I was restricted to even dimensions? And the answer is yes and no. Yes. There was another reason in odd dimensions. So the answer is yes, but it's a double yes if you wish. In odd dimensions, we'll have to discuss this point separately, whether this guy is there or not. So the claim is that in even dimensions, all the power law divergences can be trivially removed by Peskin and Schroeder techniques. This guy cannot be removed because it's an anomaly, and this guy is completely scheme dependent. I can remove it. Okay. So summary. The only physical part of the partition function is the coefficient of the log. A of lambda is physical and constant on M. Okay. Now let's do it in odd dimensions. Is this legal to do this? Can I just erase here or not? Are you going to punish me or not? No. Okay. Okay. You don't look happy. Okay. I'll. Now in odd dimensions, the power law story will be exactly the same. Okay? Okay, I'll write it again. So, sorry, log of z. So we're computing the free energy on an odd dimensional sphere now. So we're going to have now but now we start with 2m plus 1, right? Okay, and we're going to go down all the way to constant. So the last one I can get is, to f of lambda. And here there is no logarithm. Can someone tell me why there is no logarithm? But why does it vanish?
Can't write anything down dimension D.
Very good. Very good. So let me elaborate. So you would have had a log if you could have something on the right-hand side that was different from 0. Okay? But what is the dimension of T mu nu? D. We're in odd dimensions. And the point is that there is no curvature invariant, differential invariant quantity that you can construct that has odd dimensions. Because actually the curvature has dimension 2, so there is nothing you can write down. And therefore there are no conformal anomalies of this type. There could be of other types. Okay, so the power law divergences will be killed by local counter terms. So I have to tune. Okay. What about f of lambda? Is f of lambda physical now or not physical? Sorry?
Physical?
Okay, why?
You can't add counter terms.
It's essentially the same dimensional analysis argument. You will need to add something that has odd dimensions, and there is no local quantity that you can write down out of the metric and the gates and the coupling constant that has odd dimensions. So this tells us that the finite part of the partition function is physical. So now you could ask, is this a non-trivial function of the conformal manifold? And the answer is no. And the way you prove that is to essentially so it's physical and just like the conformal anomaly, and is a constant on M. And the reason that this is true essentially is that the 1-point function of an exactly marginal operator on the sphere, on an odd-dimensional sphere, vanishes. So if I take a functional derivative with respect to lambda, I bring down an O, but then the 1-point function of O on the sphere vanishes. I should say that this statement that sounds trivial is not true in even dimensions, because there is operator mixing that's possible, and we will discuss this later. And we'll have to worry about this issue a lot. Sorry?
Why are all the powers integers anyway?
That's called locality. Locality of ultraviolet divergences.
So you can't have generic operators exchange between T and Y.
All ultraviolet divergences come from some regulator. You have a very massive particle, and you do a low momentum expansion. All things that you can write down will have to be local functionals of your fields, and those have these dimensions.
You're not assuming polymorphism?
No, absolutely not. No. I'm just assuming that you have a conformal field theory so that lambda is married to R, and just use a locality of ultraviolet divergences. You cannot have lambda to the R to 7/8. That wouldn't be a local thing. So summary of this discussion. We have that in even dimensions, A is physical, and odd dimensions, F is physical. F, and both are constants. Okay? So after all this work, we seem to have arrived that this beautiful rich object, at the end of the day, only carries some little information that is scheme independent, which is just these constant functions, A and F. Okay? One thing that's important to say, nevertheless, now I don't know how much time I have to go into this, but yeah, I should. Have you heard about C theorems or not? Yes? Oh, okay. So something that's important about the sphere partition function is the well, I never used it before. Wow. You should have told me, Oliver. I mean.
I was happy for you to come back on this.
Ah, okay, I see. So you had selfish reasons. Yes. So, okay, so let me tell you how the sphere partition function in any dimension defines ordering in a space of quantum field theory, in a space of conformal field theories. So here's the idea. So let me tell you, this will be quick because, so we have some CFT that you start with. Let's call it CFT UB, and you perturb by some relevant operator. Now this will flow in the infrared to another CFT, okay? And one thing that you want to do is to try to come up with an object that defines a certain ordering in the space of a quantum field theory that tells you that if an RG flow between this theory and this theory is possible, it's not possible the other way around, okay? And this was originally done by Zamolodchikov in 2 space-time dimensions, and it's called the C function. And essentially the statement is that the C function is a quantity that decreases from the UV to the infrared, okay? Now, the thing that's beautiful about the sphere partition function is that it defines, so originally this was understood in even dimensions where you have conformal anomalies. And then this quantity that decreases along the RG flow let's call it C, had to do with conformal anomalies. The Weil anomaly, more precisely. But for a long time, it wasn't clear what was the right, if there was such an object in odd space-time dimensions where there are no conformal anomalies. And in a sense, the sphere partition function unifies all of these, and then the statement is that the log of the partition function in any dimension, the physical part, so this you should take with, I'm not being super careful about this, defines an ordering. So the sphere partition function is the quantity that defines an ordering in the space of CFTs in all dimensions, even an odd. Okay?
Would there be a -1 to the p -1?
Yes, so that's why I put the quotes. There are various signs that I'm not keeping track of. Yes?
You notice a conjecture in dimension larger?
No, in dimension than 2? No, in 3 dimensions it has been proven.
Larger than 4.
Oh, larger than 4, yes. I'm a string theorist, but I usually stick to, in field theory, I'm from 4 and lower, but yes. Indeed. So there are proofs of various types in D equals 2, 3, and 4. Okay. And actually, one more thing I can say about this. So you could ask, okay, so this is already awesome. The sphere partition function defines a quantity that gives you non-perturbative information about RG flows. It tells you a certain relation between CFTs on how you go from one to the other, and then you cannot go back. There is no deformation that will allow you to go back. But actually, you can also ask another question, which I won't have time to go into the details. You can ask, what does this compute in flat space? And this also has a beautiful answer. So I'll just tell you what the answer is, and if you're interested, you can read more. So now we're in Minkowski space. Now let's consider a Cauchy surface at t equals 0, okay? And consider a ball of radius r. So this is a region A. The complement of it, we'll call it A bar, and A is a ball. The boundary of the ball is a d minus 2 sphere, okay? Claim, and this is not hard to prove, but I don't have time to do it now. We can discuss it if people are interested. The claim is that the log, so this is only true, this statement is only true for conformal field theories again, that the log of the partition function of this on the sphere computes. So this is something that you may have seen. I saw Tom using some words like that, so I'll assume that you understood his words. Computes the entanglement entropy across the region A. Okay. So this quantity that you define in curved space answers the question about physics in flat Minkowski space. Okay, it computes the entanglement entropy. That's a very extremely popular subject in our field right now. So I just mentioned this as another example of how, in this particular context, and we'll see much more rich examples than this, where studying the partition function of the theory of a conformal field theory on a curved manifold answers a question about physics in flat spacetime. Okay. Okay. So maybe I'll try to be. Okay. Let me see. Maybe this part I can be impressionistic. At least give you a flavor of what I will continue with tomorrow. So this analysis that I did was for a generic conformal field theory with I didn't assume any additional symmetries. All I used is that my regularization preserved the diffeomorphism invariant. There were no other symmetries. Now you can ask the following question. Could it be that in a theory that has extra symmetries, i.e. supersymmetry, that there is more physics to the sphere partition function than just the Euler anomaly? Okay. So question. Can additional symmetries, in particular SUSY, endow ZSD with more scheme independent now? Why could this happen? Can someone have an intuition of what? Yes. Exactly, yeah. So we had some local counter term, and now if you have a theory that has extra symmetries, the counter term has to be consistent with those symmetries. And therefore, when you demand that your counter term is supersymmetric, the kind of counter term you may get may have lesser ambiguity, and this is exactly what happens. So let me try to describe this a little bit. Okay. So the point is that the space of counter terms, when you have additional symmetries, is reduced. Okay. So how would you tackle this question? We would have to do exactly what we did before. We have to write down all local counter terms, but now instead of imposing that, okay, so now we're in the supersymmetric world, so we have SUSY. And now in SUSY, everything comes into multiplets, as you know. So what do we have? We have a quantum field theory that lives on some curved space. So we have a metric. Now, so this would be in the bosonic world. In the supersymmetric world, we would have to embed the background field into the corresponding supersymmetry multiplet. The supersymmetry multiplet that contains the metric, it's called the supergravity multiplet. Okay. Which always includes the metric. Now, what other operator necessary? So the metric couples to which operator in the theory? What other current does a superconformal field theory have? Supercurrent. So the field that couples to the supercurrent is the gravitino. And then you can have, depending on details of how many dimensions, how much supersymmetries, you can have extra fields in your multiplet. Okay, and this is the gravitino. This couples to the energy momentum tensor. This couples to the supercurrent. Then the coupling constants of the exactly marginal operators have to embed it into supermultiplets. So they're typically embedded into bottom components of a multiplet. Are you familiar with this language of bottom and top components? Okay, so it would be a bottom component of a supermultiplet, for example, the chiral multiplet. The chiral multiplet that you've seen last week has the lowest component is a scalar, and you would embed your exactly marginal coupling as a bottom component of a chiral multiplet. And then the exactly marginal operators, they have to be obviously supersymmetric, are also in supermultiplets. But since they have to be supersymmetric, one thing that you know from supersymmetry is that the generic supersymmetric invariants are top components, because the variation of a top component is supersymmetric. So you would embed this as a top component. Sorry. It's not zero, it's whatever it is. But now I will embed like this, okay? So now what you have to do is essentially go back to the culprit of the ambiguity, this term, and ask what is the supersymmetric completion of this term, okay? So let me very quickly go through this and then I'll stop. The details of this are horrendous, but I just want to give you because you have to construct supergravity invariants, God forbid you, that you have to ever deal with that in your life. But I'll give you the intuition of how you know if the partition function acquires more physical meaning or not. Okay. So you have to essentially construct not only diffeomorphism invariant quantities like this one, but now they have to be supergravity invariant. Okay, they have to be invariant under supersymmetry also. supergravity invariance, SUSY invariance. So let me tell you qualitatively what can happen. So there are two types of SUSY invariance that you saw last week. They can be either what I call D terms, do the words sound familiar, D terms, and then F terms, okay? So if there are D terms, I'm using this a bit colloquially, but D terms have the property that essentially the quantity that you get is real, okay? So it will be a function of lambda and lambda bar, okay? It's a real function of lambda and lambda bar. So that means that if your local count, if your supergravity invariant is a D term that can affect the partition function, then Z has this kind of ambiguity, and therefore Z does not have any more physical value than in the bosonic theory, because the finite part I can shift away by a D term counter term, okay? Now the thing that gets exciting is that if you have an F term, if the supergravity invariant is an F term, then it looks like this. You remember F terms are holomorphic, right? So now I get a function F of lambda plus complex conjugate. So now what is the ambiguity? Of Z. I can add at my free will this guy to the partition function. So now Z will shift, but in this way. Now, can someone tell me of a quantity that you can define given Z as D that would not depend, that will not be affected by choice of this local counter term? Yeah, that would be an example of that. There are many other ones, but that's one. So that means that in theories in which the local counter term sits in an F term, so in this theory, so if counter term is an F term, dd lambda I, dd lambda bar j bar of log of Z of the sphere is a scheme independent. Because indeed, the choice of regularization, when I take the dd bar derivative, does not see that ambiguity, okay? And now the thing that I will prove tomorrow to connect to the beginning of the lecture is that, okay, so this guy is independent, wonderful. It is a non-trivial function of lambda. What is this? And lo and behold, what we'll prove tomorrow is that this guy is precisely the homologic metric. Which was an observable that we defined in flat space, right? So the point is that in theories in which this happens, the sphere partition function is physical, and you can extract from it the metric on the conformal manifold, the exact metric on the conformal manifold, which was what we're seeking to do. And I'll just finish by listing different examples where to tell you whether we are in this situation or this situation. So if you study the four-dimensional and equals to superconformal field theories, then Z is not more physical because the local counter term is in a D term. But for four-dimensional n equals 2 superconformal field theories, then Z becomes physical. You can compute from it. It determines the homologic of metric. So that's in 4 dimensions. In 2 dimensions, you can have theories that I will describe in detail that are 2,2 superconformal field theories. These theories are important in the study of string theory. So string theory, once upon a time there was something called string theory with world sheets and stuff. And the 2,2 superconformal field theories define compactifications from 10 dimensions to 4 dimensions. And these are theories that are anywhere in the moduli space are hard to solve. They're strongly coupled. And the point is that in these theories, Z is computable. And Z not only has an interpretation as a metric in the conformal manifold, it also has an interpretation as a term in the effective field theory of the 4-dimensional theory that you get when you compactify from 10 dimensions to 4 dimensions. So tomorrow I will continue by proving this last step, how the partition function of these theories, where Z is physical, indeed computes the homological metric. Okay, sorry, we're going over time.
Maybe one question before we go over?
I just want to make a small comment because your definition of the metric involves two marginal operators in superioris theory. It is actually f to the 4, so it should really scale as in 1 over n tau square. Yeah?
Sorry?
Like a correlation function should be really, you should really compute correlation function like O and O bar.
Yeah.
Is f to the 4.
So you have F squared with F squared, right?
Yeah, right.
So how many propagators do you have? How many propagators do you have between F squared and F squared? 2, yeah?
Sure. So it should be really 1 over n tau square.
Yeah, that's what I wrote. 1 over m tau squared, yes. But I said that the propagator between A and A is m tau, not m tau squared.
Oh, yeah, I was confused by that. Like, I was confused if you were saying about the propagator between f square and f square.
No, I was talking about the propagator between A and A is m tau.
All right, let's have our coffee break. We'll be back at 3:45. This is nice. Yeah. Oh yeah. No, I think it was a really great thing. So why is it that when you do even dimensions, you have all these even powers of lambda r, and in odd dimensions you have all these odd powers of lambda r, but you still have the even power, which is just f of lambda,
No,
right? Because that didn't have any lambda r's, right?
yeah, because the powers of lambda have to be ultraviolet divergences. They're fixed by locality, and that's just dimensional analysis. The finite power may or may not be there.
So you say that the finite part, it's not really that it's even or odd,
No,
it's that there's always a finite
yes,
part.
yes.
Okay.
Except that in even dimensions is not physical. Except if you have this extra symmetry.
So I have a question about the physicality